Welcome back to MS3. This is the next video in MS3.2, the alkane groups. So we looked at some common uses of alkanes. Now we'll look at the structure of alkanes. So as I mentioned before, they form little tetrahedral shapes. You can see a tetrahedral shape, one carbon bonded to four other atoms. So tetrahedral molecular geometry is found around all carbons in the alkanes, and as you can see here, we can rotate them. Rotate around a single bond is easy to do and occurs rapidly at room temperature. So just like if you imagine this as a ball and stick model, which is what it is, we could of course rotate this part around the single bond here. To visualize such a rotation, imagine grasping either methyl group in a propane molecule as seen on the right and rotating the group relative to the rest of the molecule. Since motion of this sort occurs rapidly in alkanes, a long chain alkane molecule is constantly undergoing motions that causes it to change shape. You can imagine it like the length of a chain being shaken. It's still a one big long length of chain, even though we can shake it and the shape looks somewhat different. Structural isomers. When you see the word isomers, think of the word versions. So versions, isomers, the different versions, the structural versions that we can see. So the alkanes that we saw previously on that one table, such as right here, table 24.2, and you'll get a copy of this. These are just one long continuous chain. So those are called straight chain hydrocarbons because all the carbons are joined on a continuous chain. Alkanes consisting of, if we have four or more carbons, we can also get something referred to as branch chains. So, for example, if I had only three carbons bonded together, there's only one way I can do that. Like even if I go like this, it's really the same thing. It's a long chain. But as soon as I get to four carbons, 1, 2, 3, 4, I can have that. Or I could take this N carbon, break it off, and attach it in the middle. And these would be two different ways of showing C4. And if I look at the H's that I would have to have here, C4H8. 1, 2, 3, 4, 5, 6, 7, 8. Let me see if I have that right. Oh, actually it's C4H10. Because 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the N pieces. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's two different ways I could actually arrange C4H10. One would be in a long continuous chain, and one would be kind of this T shape. So structural isomers, so what they have here, structural isomers have the same formula, such as C4H10, but the atoms are bonded in a different arrangement. So isomers of C4H10 and C5H12 can be seen here. So if you look really, though, it's really tiny here. So 4 carbons, just like how I have it up here, or take that N carbon, put it in the middle, and I could get this structure. If I have 5 carbons, I can do even more. So 5 carbons in one long chain called N-pentane, or the N stands for normal. Then the first arrangement, you can see it's isopentane, and then neopentane. So take one of those N's and put it in one of the middle ones. I could put it here, 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 or here, would be the same. Take another end one, put it here, and it makes kind of a cross shape. So there's 3 different isomers. So as seen here, the 4 carbons has 2 arrangements like I've shown here. C5H12 has 3 different arrangements that we can see here. And if I keep going up, the number of possible structural isomers increases rapidly when I add more carbons on. So for example, there's 18 isomers or versions when I have the molecular formula C8H18. And if I jump up to 10, when I have 10 carbons, there's actually 75 different arrangements that you could make. So when looking at naming or nomenclature of alkanes, as seen in the table, there are common names that we could use. And as I mentioned, the N being normal, that represents just a long continuous chain. We could use the prefix iso when there is 1 branch, neo when there are 2 branches, and then we can keep going higher and higher and higher. When there are more branches, it becomes impossible to come up with enough prefixes representing each isomer, so another system is used. It's by the IUPAC system, so the International Union of Pure and Applied Chemistry. Chemists everywhere, regardless of their nationality, subscribe to a common system for naming compounds. There's basically three parts. So we have the base, which is the longest continuous chain that we can make, and it comes from the how many carbons are joined in that one longest chain. And then the suffix at the end tells us what type of compound it is. So it's referring to what family. Is it the alkane family, the alkene, the alkyne? And then the prefix tells us what's attached to that chain. So what are the substituents? So there's basically three parts that make up the naming that we're going to be using. The base, which is how many carbons are joined together. The end part, which will be either ane or ene or ine. We're going to start off with the alkane family, so you'll see that they all end in ane because they'll all be single bonds. And then, of course, what is attached? What is attached to that big carbon group? So the rules, and we'll have plenty of examples here. So the key thing is to find the longest chain, the longest continuous chain of carbons that you can make. And that is going to be the base name, how many carbons. So whether it's methyl, ethyl, ethane, propane. And then we number the chain from the area that's going to get us to the attached group the quickest. So the part that's attached, what is going to get us to there the soonest? That's how we're going to enable that. And then that group that's attached, or is the substituent, is a prefix along with the number of carbons to which they're attached. The names of the substituents are going to be alphabetically. Now, so these little groups are going to be attached. They're going to be little methyl groups, little ethyl groups, or little sometimes propyl groups. And you can see here, CH4 is methane, but when we take one of those hydrogens off to make room for it to attach onto something, that is called a methyl group. And the same thing happens with ethane. Take a H off, get ready to attach it onto something. It's proethyl, propyl, butyl, etc. But when naming, we would name it in terms of alphabetical first. So this comes first, methyl comes second, and propyl will come third, assuming that I don't have a butyl group. And then begin the name with the number of carbons to which each of the substituent is bonded. Okay. Now some of these rules are going to seem kind of foreign at the start, but when we actually start naming, it'll become clearer. So we could jump in and start naming. So if I have something like this, now I wish I would have gave a few easier ones, because I have kind of like these ones that almost look like a snake. So this one here, one long continuous chain. So it's like taking your pencil and try to go through as many carbons as you can without lifting it. So if I go this way, oh, I only hit 3. But if I go this way, 1, 2, 3, 4, 5, 6. Or if I had started here, 1, 2, 3, 4. I think about the 1, 2, 3, 4, 5. Then I could go either this way for 6 or this way for 6. It wouldn't matter. I could have easily gone this way. But since I have 6 carbons, that's going to give me the base name hex. And because they're all single bonds, ane, hexane. And then I'm going to number it. Remember, I number it in such a way that I get to the first attachment the quickest. So if I had numbered it this way, 1, 2, 3, 4, 5, and there's my attachment, versus 1, 2, and there's my attachment. So I want to get to my attachment the quickest way. And the attachment, or the group here, the substituent, is not part of that long chain. Now you can see it's CH3, and of course CH3, that is the methyl group that we talked about. So it's going to be attached to carbon number 2 of the hexane chain. So I would say 2-methylhexane. So that's how we would label that. This other one here, which is a little bit confusing. Yes, the longest chain has 7 carbons, if I had numbered it this, and look at my other little groups. Here I have a methyl group. Here I have, oh yes, a C2H3. Oops, that's an ethyl group. And oh, here I have a methyl group as well. And here I have a methyl group that doesn't make up the long chain. Because here's the long chain. Circle the long chain, and then whatever's left over are going to be those substituents, those alkyl groups. So 7 carbons, of course, is hept. Since they're all single bonds, it's going to be the ane. Anything that's single bond is ane for the structure. And then I have, let's see, 1, 2, 3 methyls and 1 ethyl. But remember, we label in terms of in alphabetical order. So E comes before M. So I talk about ethyl first of all. And it is attached to carb. Now, look at how I numbered this. I could have numbered it 1, 2, 3. There's my first group. Or 1, 2, and there's my first group. So obviously I want to get to my attached group the quickest, so I number it this way. So at position number 3, at carbon number 3 is where I have my ethyl attached, so that's why I have 3-ethyl. And then at position 2, 4, 5. 2, 4, 5, I have methyls. And to reinforce the idea that I have 3 of them, 1, 2, 3, 1, 2, 3, I use the prefix tri. So 3-ethyl, 2, 4, 5, trimethylheptane. Okay, so those are some examples of how we do that. Maybe see if you can do these two. They're kind of tricky because, again, they're showing the H's branched off as opposed to the simplified way of, for example, CH3 as opposed to CHHH. But see if you can circle the longest chain, at least, in each one of these and see if you can figure what that group is. And then we'll come back and take a look at them.